You know that picture of an atom we all have in our heads? That tiny little solar system with a nucleus in the middle and electrons just zipping around in these perfect, neat circles? It's a simple image, it's clean, and as it turns out, it's not even close to the whole story. Today, we're going to dive into the real and frankly much stranger world of where electrons actually live.
Yep, there it is, the good old Bohr model. This is probably what you drew in your high school chemistry class. You've got the nucleus, and then you've got these electrons locked into these specific orbits, kind of like planets circling the sun. And look, it was a totally revolutionary idea for its time, but science has since peeled back the layers and found a much more fascinating picture underneath. So let's just get rid of it. Because here's the thing, electrons do not follow neat, predictable paths. Their entire reality is all about probability and quantum mechanics, which makes it way stranger and way more interesting than a simple orbit. So let's toss out this old model and go find out where electrons really hang out. To really pinpoint where an electron is, we need to stop thinking like an astronomer and start thinking more like a postal worker. Seriously, we're going to figure out an electron's complete address, a whole system that tells us exactly where we have the highest chance of finding it inside the huge, empty space of an atom. Okay, first up in our address is the state. In chemistry, we call this the principal energy level, and it's not a thin line like an orbit, it's a huge region, a whole shell, at a certain distance from the nucleus. An electron in energy level 1 is going to be closer and have way less energy than one hanging out in energy level 3. So, this is our first big step to locating it. Right, so within each state, you've got cities, and in the atom, these are called sublevels. Every single energy level is broken down into one or more of these sublevels. So an electron doesn't just live in energy level 2, it lives in a specific sublevel inside that energy level. See? Our address is getting a lot more specific now. And finally, we get down to the actual street, the atomic orbital. Now, this part is absolutely crucial. An orbital is not a path. It's a three-dimensional cloud of probability. It's a region in space where there's a really high chance, like a 90% chance, of finding the electron. The electron isn't on a railroad track. It could be anywhere inside that cloud at any given moment. And these streets, or neighborhoods, come in all different shapes and sizes. As you can see here, the s orbital is just a simple sphere, and it can hold 2 electrons. Then you get the p orbitals, which look kind of like dumbbells, and they can hold up to 6. And as you go further down to d and f, the shapes get way more complex, letting them hold even more electrons. Each unique shape is just a different kind of neighborhood where an electron is likely to be found. Okay, so we've got the addressing system down: energy level, sublevel, orbital. But how do electrons decide where to live? They can't just move in wherever they feel like it. Oh no, there are very strict rules of the neighborhood, 3 fundamental principles that dictate how every single atom in the universe is built. First, there's the Aufbau principle, which is a German word that basically means building up. And honestly, it's just common sense. Electrons are lazy. They want to be in the lowest energy state possible. So they always fill up the closest, lowest energy orbitals first, before they even think about moving to higher, more energetic ones. It's exactly like filling up seats in a theater from the front row to the back. Next up, the Pauli exclusion principle. I like to call this the 2 per room rule. Any single orbital, any one of those probability clouds, can hold a maximum of 2 electrons. But, and here's the catch, if they do share a room, they can't be identical. They have to have opposite spins. You can just picture one spinning clockwise and the other one spinning counterclockwise. And my personal favorite, Hund's rule. Think of this as the bus seat rule. You've definitely lived this. When electrons get to a sublevel that has multiple orbitals of the same energy, like those 3p orbitals, they don't pair up immediately. No way. They spread out. Each electron takes its own empty orbital first, and only after every single orbital has 1 electron do they start doubling up. They want their personal space. So, you put all those rules together, and you get this, an electron configuration. Now, I know it looks like some kind of secret code, but it's really just the complete address list for every single electron in an argon atom. Let's decode it real quick. The big number, that's the energy level. The letter, that's the orbital type. And that little superscript number tells you exactly how many electrons are in that specific orbital. This little line of text tells us precisely how argon's 18 electrons are arranged. Okay, I know that was a lot of theory. You're probably sitting there thinking, why does this insanely complex address system even matter? Well, here's the cool part. It turns out that for basically all of chemistry,
We only really need to care about a tiny handful of electrons, the ones living right on the edge. And these are the stars of the show, the valence electrons. These are the electrons way out in the outermost, highest energy level of an atom. They're the pioneers, the explorers, the electrons right on the frontier. And for a chemist, they're pretty much the only ones that matter. And here is the big payoff. Literally, everything an atom does is determined by its valence electrons. They're the only electrons that get involved in making chemical bonds. They dictate whether an element is a superreactive metal or a totally stable gas. In fact, this is the whole secret behind the periodic table. Elements in the same column act alike because they have the same number of valence electrons. The whole shebang. It all comes down to these outer electrons. Let's take a real-world example, sodium. It's got 11 electrons total, but after all those inner shells are filled up, it's left with just a single, lonely electron in its outermost shell. And that one valence electron makes sodium incredibly reactive because it is just dying to give that electron away to become more stable. So writing out that really long electron configuration every time is, well, it's a chore. But more importantly, it kind of buries the lead. It hides the star of the show, the valence electrons. So chemists came up with this brilliant shorthand to make seeing what's important incredibly easy. So on the screen now is the full, unabridged story for a chlorine atom. This is an orbital diagram. You can see every single one of its 17 electrons, with each box being an orbital and each arrow an electron. It's complete, it's totally accurate, and let's be honest, it's a little overwhelming. But now, look at this. This is a Lewis-Stock diagram for the exact same chlorine atom. It brilliantly ignores all of that inner core electron stuff and shows us only one thing, the symbol for chlorine, Cl, surrounded by 7 little dots. And those 7 dots, they represent its 7 valence electrons, the only ones that are going to do anything interesting. And that is the genius of it. The Lewis structure just strips away all the background noise. It focuses our attention completely on the electrons that are going to be part of the action. It's this elegant, super powerful tool that simplifies all that quantum complexity down to its most essential parts.
Now, these diagrams are amazing for showing us where electrons are. But what happens when we energize them? What happens when they actually move? Well, that's when things get colorful. When we excite atoms, like by sticking them in a flame, their electrons get this jolt of energy and jump to higher energy levels. But they can't stay up there, they fall back down, and when they do, they release all that extra energy as light, creating these specific, signature colors for each element.
So the next time you see a fireworks display, remember what you're really watching. Each burst of brilliant red or green or blue is the visible proof of billions upon billions of electrons jumping between their energy levels, broadcasting their quantum addresses across the entire night sky. Every single color is a clue. So what are the electrons telling us?